Hello everyone, and welcome to AI-RADS, an introductory machine learning course for radiologists. Our first lecture will focus on machine learning basics in the NAИVE Bayes algorithm. As an overview of this lecture, we will first introduce the framework of the AI-RADS curriculum and define some key terms. We will then explore a familiar example of a problem machine learning has tried to solve. There will be a little bit of math that we'll use to explain how NAIVE Bayes works. We will then discuss applications of the NAIVE Bayes algorithm to clinical radiology. And lastly, we will finish off with an in-depth discussion of a research article that uses NAIVE Bayes in a way that might be useful to clinical radiologists. So first, what is this class? AI-RADS is an introductory lecture series on artificial intelligence for physicians with little to no computational background. We will focus on big ideas and applications rather than raw theory. Many of the techniques we will learn about were inspired by simple observations or intuitive reasoning. The goal for you is to have a general sense of how these algorithms work and feel that this is something that perhaps you yourself could have come up with. Lastly, this is not a programming course. There are many fantastic resources that exist that can teach you how to employ these algorithms that will be linked in the description. However, the scope of this course is to provide a general overview of machine learning techniques. Each lecture will cover one algorithm in artificial intelligence. In these discussions, we will include basic concepts in computing and recurrent themes that will broadly apply to most machine learning applications. In general, lectures will first present these algorithms as solutions to real-life problems that we are all familiar with. These more relatable topics will serve as conceptual anchors for clinical approaches, which will be explored later. Lastly, a discussion of a specific journal article will reflect the algorithm in modern practice. By the end of this lecture, you should be able to describe the differences between AI, machine learning, and neural networks. You should be able to define the term algorithm. You should be able to describe the NAIVE Bayes algorithm. And you should be able to identify problems that are amenable to being solved by the NAIVE Bayes approach. On to some semantics. Throughout popular media, the terms AI, machine learning, and neural networks are used almost interchangeably, though these terms actually refer to different things. AI is the most generalized of these labels and encompasses any machine capable of responding to an input in a way that can simulate an intelligent response. This can include things as rudimentary as automated phone operators, where you endlessly click through options in the hopes of talking to a real person, to highly advanced self-driving vehicles. Machine learning is a type of artificial intelligence that uses statistics to make decisions. It demonstrates a capacity to learn from additional information or examples. The algorithms that we will talk about in this course are all machine learning algorithms. Lastly, neural networks are a family of machine learning algorithms that are loosely designed after how neurons are structured in living things. More on this later. So we use the term algorithm a lot in the last slide, but what is an algorithm? Many people think of complex mathematical equations or some beautiful mind-style chalkboard drawings where they hear this term, but in reality, you use algorithms every day without really thinking about it. An algorithm is just a set of instructions you use to complete a set task. Things as mundane as baking cakes or tying your shoes are algorithms. You follow a list of instructions and, assuming you followed them properly, you get the same end result. Today, we will discuss the NAIVE Bayes algorithm, one of the simplest classification algorithms in machine learning. Just kidding on this math stuff. Don't worry about it for now. This will make sense at the end of the lecture. Algorithms come about when we are faced with problems that need to be solved. I find that it's easiest to think about algorithms when you put yourself in the headspace of someone originally trying to solve the problem for the first time. Let's start with one of the most common and important problems in machine learning: we want to classify information into distinct categories. That is, we want a machine that, when presented with new information, can draw on its past experiences and make an informed guess as to how this new information should be labeled. Maybe you have a PACS add-on that can label chest radiographs as normal or abnormal. Or perhaps you have an add-on to your requisition template that can bounce imaging requests with insufficient clinical information. Regardless, classifying information into a distinct category is a classic problem in machine learning. Let's start with one of the most recognizable classification problems that you all are familiar with: spam filters. Since the dawn of the internet, spam emails have existed. Filtering out these seemingly endless messages is important for clearing already cluttered inboxes and presents a very interesting computational problem. Now, before we begin, most would agree that spam emails are qualitatively different than regular ones. A cursory glance at some shows that they tend to keep trying to sell you things, or may relate to Nigerian princes from far-off lands, or push vitality supplements. For this, we can reasonably conclude that some words appear more often in spam emails than normal or ham emails. This brings us to our first important observation about our classification problem. Some words are simply more likely to appear in spam emails than in normal emails. Here is a real spam email copied and pasted directly from my inbox for your viewing pleasure. As a cursory glance, it seems like this email obviously feels different than a regular email. For one, the word offer appears no fewer than 4 times. Additionally, the phrase paid keeps reappearing as well. Next, there are a number of semantic and grammatical errors that just don't feel quite right. So in summary, some words are definitely more likely to appear in spam emails than in normal emails, and certain grammatical constructs or semantic errors also seem to be more common. So how do we take all of this and take advantage of it in order to create a classification model that can separate spam from normal emails? Let's do a little experiment. Say I collect 100 emails at random, 30 of which are spam, and 70 which are ham or normal emails. So given this sample, what are the odds we get a spam email? Recall that 30 of the emails are spam and we have 100 in total, so the odds of us getting a spam email should be 30%. Conversely, the odds of us getting a ham or normal email should be 70%. Should be pretty straightforward at this point. We can express these ideas a little bit differently, where in statistics we can say the probability of getting a spam email is 0.3 and the probability of getting a ham email is 0.7. Again, these phrases are identical. In math speak, though, we express these ideas like this. So based on that original spam email I showed you guys, it seems like some words, such as offer, appear very commonly. Let's take those 100 random emails that I sampled and just search for the word offer and see how many emails actually contain that word. Let's say, for example, in the spam emails that 24 out of the 30 spam emails contain the word offer, and 10 emails from the ham emails contain the word offer. Already at baseline, we get the sense that it seems like offer appears a lot more often in spam emails than normal emails. So if we know that the email is spam, what is the probability it contains the word offer? Well, as I said earlier, there are 24 instances of the word offer in our 30 spam emails that we've sampled, so it should be 24 divided by 30, or 0.8, roughly 80%. In math words, the probability of offer, given that we know it's spam, is 0.8. As a brief explanation, P just means probability again. Offer over here means that the word offer appears. This line we'll see often, and it means basically that the next phrase is true. So reading it from left to right, the probability that the word offer appears, given that we know that the email is spam, is 0.8. This expression is equivalent to the above. Likewise, if we know that the email is ham, or normal emails, We know that 10 out of the 70 emails contain the word offer. 10 divided by 70 is roughly 1.43 or 14.3%. Likewise, we can express this idea as a probability term. So the probability that an email contains the word offer, given that we know that it is a ham or normal email, is 0.143. Now, this should make intuitive sense, right? The odds of containing the word offer is much higher if you know it's a spam email versus if you know it's a ham email. However, this is not terribly interesting to us, right? This is reliant on the fact that we already know if the email is spam or not. What we really want to know is the reverse of the question. What are the odds that an email is spam if it contains the word offer? Previously, we discussed what is the probability that an email contains offer if we know that it is spam. But what we're really trying to solve is, what is the probability that it is spam given that we know it contains the word offer? This is a little bit tricky, but fortunately someone has already figured this out for us. Introducing Bayes' theorem. Bayes' theorem simply states, or simply observes that, well, we have 34 instances of emails with the term that contain offer. 24 of them are spam, 10 of them are ham. So if there are 34 instances of emails with offer in total, the odds that an email that contains the word offer that are spam is simply number of spam emails that contain offer divided by the total number of emails that contain offer, which in this case is 24 divided by 34, which is 0.71. How do we express this mathematically? We could say then, the probability of spam, given that we know that it contains the word offer, is 0.71, exactly the problem we are trying to solve. So congratulations, we've done it. We've created a spam filter that can filter out emails that contain the word offer, knowing that there's a 71% chance that if it contains the word offer, it is a spam email. Congratulations on finishing your first lecture of AI-RADS. Just kidding. So as you can imagine, 0.71 isn't that great of a probability of being able to filter offer, and there are a lot of different words that can appear in a spam email that aren't the word offer that would suggest it's spam. Additionally, there are a lot of emails that don't contain that word that are probably spam that we would also miss. So how do we take advantage of some of these other terms or expressions that would indicate that it's actually a spam email? Let's search for a new word. Let's search for the term paid. That seems to appear fairly often in spam emails. So with a similar example, so let's say we find 5 instances of the word paid in our spam emails and only 1 instance of the term paid in our ham or regular emails. We can do a similar sort of approach that we did with the word offer. We can approach this similarly as we did before. So what is the probability that a known spam email contains the word paid? Well, we just take the number of spam emails that contain the word paid divided by the spam emails we sampled, which is 5 divided by 30, or 16.6%. In terms of probability, we can express this as the probability that an email contains the word paid, given that we know that it is spam, is 0.166. Likewise, if we know that the email is ham, the probability that it contains the word paid is 1 divided by 70, or 0.0143 or 1.43%. And in probability terms, the probability of paid, given that we know that it is a ham email, is 0.0143. Again, however, we are trying to infer what are the odds that an email is spam if it has the word paid. We can again use Bayes' theorem to answer that reverse question that we're really interested in. We note that there are 6 emails in total that contain the word paid in them. 5 of them are spam, 1 of them is a normal email. So the probability that an email that contains the word paid is spam is simply 5 divided by 6, or 0.833 or 83.3%. That is, in probability terms, the probability that an email is spam, given that we know that it contains the word paid, is 0.833. This would mean then that if we get a random email that contains the word paid based on our sampling that we have shown, there's an 83.3% chance that it is spam. Now, this is all well and good for emails that contain only one word. However, from experience, most emails contain more than one word. So what about an email that contains both the words paid and offer? Using the approach we did before, how do we determine the probability that an email contains both of those words at the same time? It doesn't seem unlikely that a word could contain both. This is where the naive Bayes algorithm comes in. The naive Bayes algorithm simply states that we can naively assume that features are completely independent. That is, an email with the word offer has the same probability of containing the word paid as any other email. Many of you may be thinking, that isn't really how the English language works, and this isn't a great assumption. And you'd be absolutely correct. This is a naive assumption. This is a bad assumption. However, for the purposes of this algorithm, we assume that it's true. We can then use Bayesian statistics to calculate probabilities. Here is a summary table of everything we discussed. So in total, we have 30 spam emails and 70 ham emails. Offer appears in 24 out of the 30 spam emails and 10 of the 70 ham emails. Paid, likewise, appears in only 5 of the 30 spam emails and only 1 of the 70 ham emails. So intuitively speaking, emails that contain the phrase paid offer seem to be much more likely to be spam than regular. However, it would be great if we could put an actual number to this. So using the same approach that we did before, we want to calculate the probability that a known spam email has both the terms paid and offer. We know from before that the probability that an email contains the word offer, given that we know it's spam, is 24 over 30 or 0.8. Likewise, we know that the probability that a known spam email contains the word paid is 5 out of 30 or 0.17. So, given the naive Bayes algorithm, we naively can assume that these probabilities are independent. So, the likelihood of both of these events happening at the same time is simply the probabilities multiplied together. So 0.8 times 0.17 is 0.13 repeating. That is, in terms of probability expressions, the probability of paid and offer appearing, given that we know it is spam, is 0.13 repeating. We can do the same thing for ham emails, where the probability of a known ham email containing both paid and offer ends up being 0.002, a very low probability. Now for our classic reverse question. What is the probability that an email with both the words paid and offer is spam? We can look back to Bayes' theorem and see what we can try to do, but again, we don't really have a true count of the number of emails with both the words paid and offer. We have counts of each individual word given our summary table, but we don't actually have a true measure of the number of emails with both. So since we don't have direct counts of emails with both, we really need to estimate this. So recall, given our probabilities, the probability of having both paid and offer, given that we know it's spam, is 0.13, and the probability of having both paid and offer, given that we know it's ham, is 0.02. What we can do with this information then is calculate an expected value. Recall that our expected value is just the probability of an event times the number of events that happen, and that expected value is the expected number of events to occur. So let's estimate the number of emails we're expecting to see in each category that contain both paid and offer. Since the probability that a known spam email that contains both paid and offer is 0.133, and we have 30 spam emails in total, we can estimate that roughly 4 of these emails will contain both. Likewise, since the probability that a known ham email contains both paid and offer is 0.002, and we have 70 ham emails, we estimate that 0.14 emails that are ham will contain both these expressions. Now that we have real counts that we can turn to, we can use Bayes' theorem to estimate what is the probability that a brand new email that is unlabeled that contains both paid and offer is spam? So if we expect 4 spam emails to have both expressions and 0.14 ham emails to have both expressions, we can calculate the probability that having both is spam as the number of spam emails that we estimate divided by the total number of emails we estimate, or 4 divided by 4 plus 0.14, which equals 0.966. That is, if an unknown email contains both paid and offer, we have a 96.6% chance that this email truly is spam, given the 100 email sample that we've learned from. At face value, this doesn't seem very impressive or particularly interesting, but I promise that there are really exciting applications of this. Before talking about why this technique is actually useful, there are a few observations I want to point out with just some quick notation stuff. The way the algorithm is set up, your classifier will never be 100% certain. This is actually kind of nice, as it reflects trends and uncertainty in data and is more representative of reality. Next, the way this is set up, you can also add terms indefinitely and just multiply the individual probabilities to spit out a final probability. This allows for a near limitless number of features to contribute to an overall outcome. Lastly, the entire premise of this algorithm is based on naive assumptions. This is both a blessing and a curse of the naive Bayes algorithm, which we'll talk more about later. Here's Bayes' theorem in its full statistical glory. Now this looks rather intimidating, however, remember, we've already done this multiple times. We're going to go through it step by step in the next couple of slides. So recall that our problem was, what is the probability that an email is spam given that it has some combination of words? In statistical terms, or in probability words, we say probability of spam given that we know that words are present. Let's break it down step by step using the example of the spam emails we talked about earlier. On the left, in the orange box, we have the probability of A given B. This is our target probability, and from our problem, remember, it was, what is the probability that an email is spam given that we know that it has some sequence of words? In the green box on the right-hand side, we have this expression here, the probability of B given A. Remember that when we were doing these calculations, we always initially figured out what was the probability that if an email was spam, what are the odds that it had a particular sequence of words? That is, there was that forward problem that didn't seem very helpful at the time, right? What this really tries to get at is, what is the incidence of words in the particular category of interest that we have? We want to know that if we know that we have a spam email, what are the odds that a known spam email will have the certain sequence that we're interested in? Next, we have this in the blue square, probability of A. Now what this just represents is the proportion of our total data set that has our category of interest, which in this case is spam. Together, the green box and the blue box represent the expected value that we talked about earlier. Remember that the probability of B given A is just the probability that a spam email will have the sequence of words, and the probability of A is just the proportion of our total data set that is spam in general. So when we multiply them together, we really get the total proportion of spam emails that will contain the sequence of interest. Lastly, we have our denominator, probability of B. And really what this gets at is, what is the incidence of B, or how many emails in total contain the phrase that we're interested in? Remember earlier that when we calculated and we estimated the number of spam emails with a particular word, we also wanted to estimate how many emails in total had that particular sequence of words. And that's really what this is just getting at over here. In terms of probability speak, we then say the probability of spam, given that we know that an email contains a certain sequence of words, is equal to the probability that the certain sequence of words exists in a known spam email times the proportion of spam emails divided by the total number of emails that contains this particular sequence of words. Here's an image again of the naive Bayes algorithm. Now this also looks really intimidating, but before we go into this more, let's actually more formally talk about what are the specific steps in the naive Bayes algorithm that will get us to solve the problem that we're actually looking for, a classifier that classifies based on probability. So for the setup for the naive Bayes algorithm, we need to have a pool of data in which we've already categorized it, and we have features that we can use to calculate probabilities off of. This was that pool of 100 sample emails that we talked about earlier. When we're given a test data point, and in this example, a new email, what we first want to do is calculate the probability that that particular test data point belongs to a specific group or category. That is, we want to calculate what the probability that this new email is a spam email. We then want to repeat this calculation for every possible category, and in this example it would be, what's the probability that this email is a ham or a regular email? Whichever category has the highest probability, we say is the winner. The answer that is the most likely solution is the one that our machine selects. Graphically, it looks a bit like this. We have some unknown email, and we have a set number of categories, spam or not spam, and we calculate the probability that it belongs into each of these possible categories. We then compare the two, and we say whichever probability is the highest is our solution. More generally speaking, we have a piece of unlabeled data that we'd like to assign to a specific category. This data can be described by features which can be expressed as probabilities. Because we say these features are all independent, we multiply these probabilities together to get a net probability that this data belongs to any individual group or category. We then compare these probabilities and say whichever group has the highest probability is the one that our new piece of data belongs in. Let's break down the formal mathematical expression for the naive Bayes algorithm. Argmax just means take the biggest number. K with that E looking thing and that set just means test every possible category. So what we're going to do is we're going to test every category, and from those categories take the biggest number that we have. Makes sense, right? Now we have this expression in purple. This purple box, if you squint a little bit, it looks awfully similar to the numerator for Bayes' rule. And if you actually look, you can substitute these directly. That P of C sub k is pretty much the same thing as P of A, and that P of x sub I, given that we know that C of k is true, is the same thing as probability of B, given that we know that A is true. So these values are actually the same. We'll talk about that in a little bit, why these look just a little bit different than what we're used to, but trust me now on this one that these two expressions are really equivalent. We then have this pi looking symbol with an n above it and an I below it. And the only thing that this means is multiply all the probabilities together. So what this n and this I is really getting at is we have a series of possible probabilities, and what they're referring to are the features that we have. So we're going to take each of these features. In the case of our emails, whether the word paid or offer appeared, those would be features, and multiply the probabilities of these features existing within our category of interest, and we're going to multiply them all together. Then we're going to test them against every category and take the biggest number, and that's it. That's the naive Bayes algorithm exactly as we described it in the slides earlier. Now many of you are probably wondering, what happened here? What happened to this probability of B occurring? And what happens here is probability of B actually drops out because it remains constant. This probability of B, remember, is really just a way of saying what are the total number of emails that contain both paid and offer, or what are the total number of, what's the total incidence of our particular features of interest. And, because we're comparing everything across categories and we're all basing this off the same data set, this is the same for every single category. This is the same for every single possible label we assign. So when we're comparing these, we're just comparing the same terms, so these all drop out because it remains constant. So, the naive Bayes algorithm, one of the simplest algorithms in machine learning. We have some unlabeled data. We calculate the probability that it belongs into some sort of category using features that describe it that can be expressed as probabilities. and we say that the highest probability category is the winner. Now, a brief note on probability. We're not going to go into a ton of detail on this because we really kind of talked to death the point of probabilities, and I'm sure all of you are dying to know how do we actually use this in radiology, but before we go on, it's important to note that probability can be calculated in many different ways. Here's that spam email again that I directly copied and pasted from my inbox. Notice how the word offer appears 4 times. In our earlier approach, the only thing we did was we searched how many emails contained the word offer, and that was it. We really didn't care how many times the word offer appears. However, intuitively speaking, it makes sense that an email that keeps soliciting offers, or an email that keeps saying the words cheap and buy and supplement, etc., is probably more likely to be spam than an email that says it once. So there must be a way of expressing this somehow also as a probability, right? This sort of frequency idea. And in fact, we can do it this way. So as I said, we have the word offer that appears 4 times, and we have a total of 147 words. So what we can do for this particular email is see the frequency at which the word offer appears in this particular email. And in this case, it's 4 divided by 174, which is equal to 0.023. What happens then if we look at a whole bunch of spam emails, similar to what we did earlier? We can take this information and make a frequency distribution of the rate in which the word offer appears in emails. We can describe this population in terms of standard deviation, means, etc. Recall that from a distribution, you can actually calculate the probability that a particular individual item appears in it. This is important because we can now relate the idea of individual examples against overall demographic information, something that is very powerful when used with naive Bayes, which treats everything like probabilities. So why do we care about any of this? We've talked a lot about probabilities and emails and words, but we really haven't talked at all about how this could possibly relate to anything radiology. The main takeaway is that almost anything that can be represented as a probability can be employed by the naive Bayes algorithm to create a predictive model. And as we just showed, the naive Bayes model can utilize bell curve information and overall population demographics to generate probabilities. So, what are radiologists good at doing? Well, the basic job description is describing what you see. As radiologists, we are expertly trained to describe what we see. These descriptions of radiographic findings are, by and large, fairly consistent across providers, which means that the naive Bayes algorithm can be used to draw associations from the frequencies in the words that we use. Prashad et al. Demonstrated that using naive Bayes over key terms and phrases in over 300 radiology reports describing colon adenocarcinomas, multiple terms are highly correlated, as in the figure below, with specific pathologies. Patients whose reports contained all 4 words associated with KRAS mutations had lower than a 1% chance of not having the mutation. Likewise, there was a lower than 3% chance that a patient with a report with all 4 words associated with the wild type was KRAS positive. Though this paper is a proof of concept, the generalized application of such can be clinically useful when linking radiographic images with genomic screening. Assad et al. Utilized a very similar approach to how we made our spam filter with the naive Bayes algorithm to create a model capable of delineating radiology requisitions that contained insufficient amounts of clinical information to accurately protocol. The naive Bayes algorithm is popularly used in text analysis due to its simplicity and its often surprisingly powerful results. However, there are a number of other applications of it, as delineated in the studies listed here. The link will be present in the description. Later on in this talk, towards the end, we'll discuss another paper that uses the naive Bayes algorithm to delineate different kinds of bone tumors. But first, before we delve into this, Let's talk about some of the shortcomings of the naive Bayes algorithm. As the name implies, the naive Bayes algorithm is far from perfect. As you can imagine from its simplicity and its extremely naive assumptions, the naive Bayes algorithm really is not very good at describing complex relationships and has a hard time teasing these out. As you can imagine, if terms are interrelated or things are changing over time, or they're simply more complicated tasks, naive Bayes starts failing. Additionally, we must know our training information a priori. This is a common feature amongst machine learning problems, and it's important to know that some algorithms require a ton of data to be effective. All of this data needs to be hand marked, hand categorized, and then eventually fed to the model. As you can imagine, in sets with tens of thousands of pieces of information, this can get quite cumbersome quickly. Next, the algorithm is relatively inflexible. While certainly you can update and adjust your training data so that the model has different information to base its probabilities off of, and you certainly can change the features in which you calculate probabilities from, this is pretty much set in the stone once you set the Excel sheet with all of your information on it. Lastly, of the other algorithms that we're going to talk about later in this class, the naive Bayes algorithm is comparably one of the weaker classifying algorithms for the reasons described above. Hopefully, this makes a bit of intuitive sense as well. Given the numerous weaknesses inherent to naive Bayes, why do we even use this algorithm? Well, Krusty the Clown has our answer for us. As it turns out, much of machine learning is making compromises between speed, flexibility, and accuracy. And in many situations, such as in rapid screening processes, good enough is just that, good enough. It's acceptable. We will now take the next few minutes to discuss this paper written by Dr. Zhou et al. And our colleagues at Stanford University. In this article entitled Bone Tumor Diagnosis Using a Naive Bayesian Model of Demographic and Radiographic Features. So again, as a 10,000-foot view of the overall lecture, we want to classify information into discrete buckets based on its features. If these features can be represented as probabilities, we can use statistics to help us out. We can use Bayes' rule and naive assumptions to link these features and probabilities together and calculate an overall probability that a piece of information lies within a particular group. We then say the category with the highest probability is the winner, and that is the label we will assign. Zhou et al., bone tumors and the naive Bayes model. So we start with a bunch of bone tumor cases, and we have two musculoskeletal trained radiologists to read each case and analyze them using a standardized tool. What we're going to do then is take demographic information from a bone tumor reference book. We've got bell curves, etc. from this information book, and what we can do then is use this information to evaluate the probability each individual feature of a case belongs to a particular class. What this means is we can take specific features of a bone tumor and compare them against demographic information against a bunch of different other kinds of bone tumors and try to figure out what category is this bone tumor most likely in. That is, what is the most likely bone tumor I'm looking at right now? As the naive Bayes algorithm dictates, we're going to take all of these feature probabilities that we've looked up for this particular bone tumor and generate the overall probability of that tumor being in a particular category or having a particular label. We're going to repeat this for all of our categories. And then, in this particular paper, what they did was, rather than return the top number 1 solution, they returned the top 3 diagnoses, the top 3 most likely diagnoses given the naive Bayes model they created. Here's a table of the features they used to describe each bone tumor radiograph. These include age, gender, number of lesions, etc. And what they did was they broke them down into individual sort of categories as indicated on the right-hand side. They then developed a tool by which the reading radiologist could enter all of the features of a given study. The diagnosis behind each scan was confirmed with cytopathology. Here is a list of the 29 most common diagnoses that they saw. They then grouped these by order of frequency, where Group 1 were the most common diagnoses, Group 2 were uncommon, and Group 3 were rare. From this, they generated 3 cohorts. Cohort A was the most inclusive and included common, uncommon, and rare diagnoses. Cohort B utilized only the common and the uncommon diagnoses. And Cohort C only included the top 10 most common diagnoses. The authors displayed some raw outputs of the calculations that their naive Bayes classifier created. Notice internally a bunch of probabilities related to individual features. These probabilities were all multiplied together, and then they were normalized to create a top 3 differential diagnosis. They then tested their model against the cohorts described earlier. Recall that Cohort A is the most inclusive and includes common, uncommon, and rare diagnoses, while Cohort C only includes the top 10 most common diagnoses. Primary accuracy in this case refers to the model's ability to return as its number 1 diagnosis the actual correct diagnosis, whereas differential accuracy refers to if the model was able to say within its top 3 differential the correct diagnosis. The paper then concludes with specific examples of tumors that the model struggled to classify. In summary, this paper demonstrates a very strong proof of concept of a practical use of the naive Bayes algorithm in clinical radiology. As a major takeaway, with this particular data set, this approach was able to achieve an 80% top 3 differential diagnosis accuracy for the top 10 most common diagnoses. In fact, an online portal still exists where one can check out this today, link below in the description. Disclaimer: there were some statistical maneuvering happening so that features didn't outright exclude some diagnoses if they didn't appear, so that the probability wouldn't drop to 0. This isn't a super important point, but just something to keep in the back of your head. So congratulations, you made it. You slogged through a lot of math and are now familiar with your first algorithm in machine learning. Hopefully now you see some practical applications that you might be able to employ using the naive Bayes algorithm and probabilistic-based approaches in labeling and categorizing information. As a reminder of the learning objectives, hopefully by the end of this you were able to describe the difference between AI, machine learning, and neural networks, define the term algorithm, describe the naive Bayes algorithm, and identify some problems that might be solved by naive Bayes. Up next, we'll talk about the k-nearest neighbor approach and start working on pixel mathematics.